how it's separated now, guys? Okay? You see that? But it's still going up, away from the Earth, Rachie. It's decelerating, but still going up. Now, which way is it showing? Maybe I have to do it this way. Okay, this was how it looked now. This is how it used to look. Okay. Now, what's the difference here? This is very simple stuff. Yeah, it's mixed up. Look how it's raised, okay? The water
Everywhere.
is at the bottom. Let's say the water's showing up then. This is going opposite direction.
Exactly, proving the point. When the acceleration is up, when there's a force up and acceleration up, the denser liquid, the denser stuff, congregates at the bottom. And when there's a deceleration in this case, aka an acceleration down, because deceleration is just acceleration in the opposite direction, so when there's an acceleration down, the denser stuff goes to the top. So if you was to let an object go, if you was to let the density tower go, if you was to let a container with different density things in go, then the denser stuff should go at the top. If it was accelerating, proving my point.
Which way is the rocket going, people? Up.
Yeah.
So it's going against your accelerator force, Rachie. Why? Because conservation of momentum. Everything has an impulse. So while it was still going up and decelerating going up, it still had a force attributed. The thing is, as soon as it hit the burst, where that accelerator force now started becoming decelerator force, it's all the things inside the vial had the same amount of force, the same impulse, even if it was for that split second.
What do you mean for that split second? If RDD was acting on it, acted for a split second, what force are you on about that only acted for a split second? RDD or something else?
So then, because it had conservation of momentum, with more mass, it moved upwards. And that's why this has done what it has. Not because of your accelerating Earth, but because of impulse. RDD shown to be true with demonstration. And taking your nonsense, idiotic, accelerating, moronic disc to the dustbin. I don't know how more clearer I can make it for these people.
What?
You think that proves RDD when RDD says more dense down relative to the medium and less dense up relative to the medium? Just because it's still moving up relative to the Earth does not mean that it needs to have a force attributed to it. It's called momentum, you know, it had an acceleration going up, therefore the speed was increasing as it was going up, and then the acceleration stopped, and it was keeping that momentum, that speed that where the acceleration stopped. Depending on what that speed was, it's keeping that speed, and then it's starting to decelerate because of drag. It can still be moving up without a force. It's because it still has momentum.
We've got the altitude plot in relation to the video. Now let's look at the right tube in slow motion. At launch and during acceleration, the water is held at the bottom.
At launch and acceleration, the water is held at the bottom. So while it's accelerating up, the water is held at the bottom. Again, so if it was accelerating up, the water would be at the bottom, just like this case. At launch, during acceleration, the water is held at the bottom. So while it's accelerating, the relative density disequilibrium still seems to work. The more dense ends up on the bottom, the less dense on the top. Yet you claim when it's accelerating down, we can't get more dense on the bottom and less dense at the top, which, because they're all accelerating at the same rate, right? So for some reason, when we accelerate up, the relative density disequilibrium seems to work with the more dense down, less dense up. But when we drop a bottle and it's apparently accelerating down, we don't see more dense to go down and less tends go up. So again, that debunks your RDD.
But as soon as the rocket stops producing thrust at burnout, the rocket is effectively in 0G except for the air drag on the rocket.
So as soon as the rocket stops producing thrust, aka stops accelerating, it's effectively in 0G, as they would call it. So now that there's no acceleration up on it, the relative densities don't seem to be relative density, move according to relative density. They seem to be moving in the opposite way. Because now there's a deceleration on it, there's drag on it now. So obviously deceleration is acceleration in the opposite direction. So now there's an acceleration in the opposite direction, so now they're flipping. Where you end up with more denser at the top and less dense at the bottom. Because there's an acceleration now down on it, aka drag, which is deceleration, which is acceleration in the opposite direction. Because there's no acceleration up on it anymore.
But let's listen to what he has to say. Now you'll hear why he says relative density is false and why he claims his claim that's not a claim is working.
Right. Gonna make these videos again to try and address some of the issues that people are having. Okay, so this is in regards to stationary Earth, so that we can hopefully get some clarity on the whole thing for people. Right.
Aye.
So stationary Earth has massive problems. First and foremost, the Earth's not a globe, right? And just because the Earth's not a globe doesn't mean to say you stop thinking, stop asking questions. There's many things that people don't comprehend, myself included, and it's a learning curve, a lot of stuff. But one thing's for sure, I accept reality for what it is and what it demonstrates to me, and the only thing that I can go by is demonstration.
Yeah. And your demonstration goes against your argument. I mean, we've drawn this out before. He claims that something in free fall, let's see if I can do it this way. I might have to do it two ways. Let's have a bowling ball for this. This bowling ball was picked up. Okay? He claims the Earth is moving at a constant speed towards that bowling ball. So as soon as you let it go, that bowling ball is at 0G. Okay? That means it has no force. The Earth is rising up at 9.8 meters per second. Okay? Second squared.
No, as you just said, he claims a constant speed. Now you're saying he claims an acceleration because you're saying 9.8 meters per second squared, 9.8 meters per second. That's not a constant speed, like you just said he claims. 9.8 meters per second is an acceleration. 9.8 meters per second squared is an acceleration, not a constant speed.
As it's going up to meet the ball. Okay? That's what he's claiming, correct?
Mm-hmm.
Okay. So, Del, what is the issue here? He's claiming that this ball is decelerating to the ground. So in other words, it has no force, it's not moving. Great.
He's claiming deceleration of the ball. Therefore, he's claiming that the ball is losing the speed that it had from the Earth. So the ball is losing speed. Decelerating.
Okay, let's take the same logic now. Let's take his bottle experiment. But let's just change it now to a brick wall. We're going to have a brick wall here, and we're going to have a brick wall here. This one is 200 meters away. This one is 10 meters away. Remember, they're sitting still, they're static. Now we got a car that's going to drive and accelerate to them. Let's say going 1,000 miles an hour. Okay, that's a bit much. Just say 50 kilometers an hour. Doesn't matter. If this car comes here and it hits that wall at 10 meters, it's only traveling at a constant 50 kilometers an hour. It will hit it at the same amount of force that it would hit that one at 200 meters away. Because why? When it hits it, it's only traveled 50 kilometers an hour. Same amount of force. Same as that, 50 kilometers an hour. So it doesn't matter the distance because the object is not moving. Remember, Del? Hi, Rachie. Yes, that's exactly his claim, Rachie, because we actually showed him making that claim.
The signs are stationary. They are not decelerating. Therefore, it is not his claim. The signs would need to be decelerating, aka moving, decelerating. This is not representative of his claim because he claims the objects are decelerating.
Rachie, you making the claim it accelerates. He makes a claim that it's constant. And his argument of why it's constant is because of rotational vector.
What?
Okay, maybe we can redraw it on paint. Maybe that'll be easier. Okay, I'm going to draw it from the side again. This is his accelerating Earth. It's supposed to go this way. Okay. But a rotational vector is that way. Now we draw it from the top. I hope you're paying attention, Dal. Because this is your claim. A rotational vector is always going to change. Oh, what the hell? It's always going to go in a different direction. But what is the issue here, Dal? Why you say, oh, why was it not working? Well, because you see here, this is the top of your pizza. That means the rotation going that way, having different vectors constantly because you want a constant acceleration, is not going to work on your disk because the disk is supposed to be going up this way. So if it's going constantly at 9.8 meters per second, whatever, squared, it would be an acceleration. And if you're going constant, then it's no more acceleration, correct? And his claim is specifically an acceleration causes the pressure gradients. That's why we say Earth is moving upwards. And I'm here to tell you, Dal, it doesn't work. Based on simple physics, that doesn't work.
Again, not what Del is claiming. You misunderstand.
Being claimed that this moves through space. So this is being claimed to accelerate, to move, motion. What have we established? If somebody claims motion happens, we need something that pushes on it. Right? No such thing as pull. Only push. Pressure makes stuff move. So if this was to be accelerated in any direction, we get displacement of the gas in the liquid. In reality, when I let this go, there is no displacement. So acceleration, if I accelerate it in that direction, the liquid moves to the back and the air towards the direction of acceleration. So here, if somebody's going to claim this accelerates downwards, then this moves to the top and the air should move to the bottom. That's what happens in the case of acceleration. But people don't want that. They want to try and come up with woo-woo, globe-type, nonsensical gibberish about some magic. So this magic freezes the plastic, the air and the liquid together so that it's accelerating all at the same time, just like a solid, with no displacement occurring. Yet we do not witness that anywhere in reality. It's not accessible to human beings. It's pseudoscience, it's gibberish. No acceleration on the downward vector. None. No. We get to people like the ones that were talking last night, just the displacement. You do not get to request special tractor beam Star Trek type accelerative forces where it applies enough force on the gas, enough force on the liquid, all varying, forces to make it appear like a solid. That's absolute fucking hogwash. I'm sorry, I tried not to swear, but I'm sick of it. It's ridiculous. And it's really embarrassing. So now we've got, by some, magical means, or it's the Earth that meets it. Now, when I'm saying that that it's the Earth that meets it, so we can have other possibilities, right? So, you know, if I swing this and have a centrifugal effect, this was the other thing, right? People arguing about the centrifugal force, right? And that centrifugal is a fictitious force and these types of things. Centrifugal effect is a result of motion, right? Motion is the cause of what we call centrifugal. So if I rotate something, I have to apply a pressure to it, right? A leverage system has to be there in order to put something in a rotating frame, right? Now in that rotating frame, which is caused by motion, pressure being applied to it, right, we get a centrifugal effect. So people who've been in a roundabout know this, that when you're on something that turns like that, you get this outward, push, this feeling of being pushed outwards. That's an effect of the motion. You don't get the centrifugal effect until pressure puts it in motion, right? And then we get a centrifugal effect. So, if I was to swing this, right, at a central point in a circular motion, we would get a centrifugal effect in that direction, okay? Like swinging a bucket. If you swing a bucket with water in it, the water will stay to the base of the bucket, regardless of what way you're spinning it. You can be spinning it in any direction and it will stay, right? Now there's issues with the postulation of it being some sort of centrifugal in that manner, where I'm swinging it and it's here. But if I have an arm like this, so that the flat's here and it's rotating like this, then there's our vector. Now you have an opposite and equal of that vector. So this arm can be tethered on a rotation, right? That's a constant acceleration because it's a constant change in direction, which would give us on the reference frame our directional vector. We would have density layering, where the most dense is compact to the bottom, the least dense at the top. Okay, depending on how fast that thing's rotating dictates the weight of any given object within that frame of reference. Okay, so if I speed it up, things within the frame of reference are going to get heavier, what we call weight. It's going to increase. Okay, other possibilities. You've seen the copper coil with, the battery and the magnet in it, and you put it in and it continuously moves round. Well, the flat face of that there would be your frame of reference for our vectors. There's loads of different possibilities. Look, I don't know what's outside the reference frame. Nobody does, right? But I'm telling you, from within the reference frame, we can establish exactly what is going on. People who are telling you cannot are bullshitters. You've got people telling me that I'm talking rubbish by practical example, which they don't have, who are saying, well, you'll never know because you can't get outside the reference frame. But I can tell within the reference frame what's going on. These people who are asserting that they are stationary, the same can be applied to them. They cannot exit their reference frame. So how do they get by saying it's stationary? The physics within the reference frame are showing that it is in no way, shape or form possible that it's stationary. Unless you've got pseudoscientific magic of something, given as the downward vector, which is a push from above. Because you need push, again, in order to say that goes towards the ground by a force. You need something pushing down upon it.
Okay, so Rachie, if you're still here, this bowling ball, okay, is denser than the air around it. Now we're going to explain this with impulse. Okay, the gas is hitting this bowling ball constantly from all directions. Okay, so it has a less force, impact force, than the bowling ball. So the impulse is very low. Okay, it's boom and it's away. It's a quick impulse because the time it has a collision is very low, and because it's less dense, it cannot support the bowling ball. So where does the bowling ball have to go? Back to its equilibrium, because at the moment it's at static equilibrium. That means I'm holding the bowling ball. Now as soon as I let it go, what is going to happen? There's nothing here to support it.
1. Why does it need supporting? And 2. There's nothing to support it to the right or to the left or up either, so why down?
I picked the bowling ball up from its equilibrium, its static equilibrium. I picked it up through a medium that cannot support it. Do you understand? So the impulse here is different. The bowling ball has a different impulse to the air than what the air has to the bowling ball. So when you take my hand away and the gas cannot support it, it will force itself through. Because when you have an impulse measurement, it means there's a force present. F equals ma. We see the ball go down, which means the mass is accelerating. That requires a force. So therefore we see the ball go down, means there's a force.
So what force is pushing it down?
You guys claim there's no force when things go down. In other words, you contradict physics.
No, it doesn't contradict physics. It's like if you was to accelerate a car, but you left the boot open and stuff come flying out the back. What force pushed the stuff out the back of the boot? There was no force, was there, pushing the stuff out the back of the boot? Yet they went flying out the boot. Didn't mean that there was a force pushing them out the boot though, does it? That there was a physical force pushing them in the direction out of the boot. No. Same way with Coriolis. Just because you see a deflection on a merry-go-round doesn't mean that a force actually deflected the ball, does it? No, because the ball actually went in a straight line. Just because you see something accelerating doesn't mean it actually is accelerating. It might not be, like the Coriolis example. Like the things flying out the back of your boot example. Doesn't mean there's an actual force on it. Like when you're accelerating in your car and you feel like you're getting pushed back into the seat. Does that mean there's a force pushing you backwards into the seat? That there's a force coming on you from the front of you, pushing you back? No, of course not.
Now we come with a straw man. Oh, when you drop a water bottle and you have water and gas, why are they not separating? Because you make a claim, RDD claims they have to separate while free falling. Bullshit. Tell us anywhere where anybody said they have to separate when free falling. Has anybody made that claim before for RDD?
Okay, so this is a bottle and we're holding the bottle. It's got water in and there's an air bubble rising through the water according to relative density disequilibrium. Because it's less dense than the water, it's rising through the water. We now let the bottle go and it's no longer rising. It's no longer moving. It's no longer doing what RDD says it should do. It's still less dense than the water around it, yet it's not rising. Why? This object in the water is less dense than the water. We are holding the water bottle. The object that is less dense than the water is rising according to relative density disequilibrium. Because it's less dense, it rises, right? It's rising through the water as we're holding it. We let the bottle go, and now it's no longer rising. It's staying where it was when we let it go. Why? This object is more dense than the water. We are holding the water bottle. The object is going down according to relative density disequilibrium. It's more dense than the water. It's going down. We let the bottle go. It is no longer falling through the water. It is no longer going down through the water, even though it's still more dense than the water. Why?
Now, when you take that whole bottle and you let it fall, what is Newton's third law, guys? Equal and opposite reaction.
Okay.
When a car is driving, the wheel exerts a force in the reverse direction on the road. At the same time, the road exerts a force in the forward direction on the wheel. These two forces are equal in magnitude, but opposite in direction.
So, have they ever heard of net forces before?
Yep.
So the net forces are zero, as they claim, when it accelerates. So why would you expect it to separate where this net force is exactly the same as that net force, the same as that net force? They all have zero net force.
What happens with zero net force? Newton's first law. If no net force, aka zero force, zero net force, no net force. If no net force acts on an object, it remains at rest, if initially at rest. So, if I'm holding a bottle with contents in, and it's at rest in my hand, and I let it go, and there's no net force, then it will remain at rest. So why then is it going down?
Where this net force is exactly the same as that net force, the same as that net force. They all have zero net force.
The net force is the vector sum of all the forces that act upon an object. That is to say, the net force is the sum of all the forces, taking into account the fact that a force is a vector and two forces of equal magnitude and opposite direction will cancel each other out. So, two forces of equal magnitude and opposite in direction. So what are the two forces that are equal in magnitude and opposite in direction in this scenario?
The same amount of force attributed to them because they accelerate at the same rate. I can't believe we have to teach this to bloody... Okay, I'm going to give 2 blocks. Okay? The one block, let's say, will be a 5 kilogram block. And the other one, a 100 kilogram block. Now when you try and push it, let's try and push against this. So we're putting a force on there, okay? You would agree it would take more force to push the 100 kilogram block than it would be to push the 5 kilogram block. Yep. Yeah. The same amount of force attributed to them because they accelerate at the same rate. So we're putting a force on there, okay? You would agree it would take more force to push the 100 kilogram block than it would be to push the 5 kilogram block. Yep. Yeah. The same amount of force attributed to them because they accelerate at the same rate. So we're putting a force on there, okay? You would agree it would take more force to push the 100 kilogram block than it would be to push the 5 kilogram block. Yep. Yeah.
You do not get to request special tractor beam Star Trek type accelerative forces where it applies enough force on the gas, enough force on the liquid, all varying, forces to make it appear like a solid.
So therefore impulse explains us having a force because of its density variations. The forces attributed are now just the same because they're both accelerating together at the same rate. There we go.
Please.